The last subject we're going to look at now in this particular chapter is we're going to look more at solids. And we haven't really talked about yet the ion-ion force or the metallic force and how they apply to the intermolecular forces. And that's what we're going to look at. So solids, when you think of all the solids in the whole world, there's basically two groups of solids. There's crystalline solids, which are just when you have the particles of the solid in highly ordered arrangement, so they are predictable in how they go together. But you also have what's called amorphous solids, and amorphous solids are more randomly placed together. The science and the understanding of amorphous solids is much more difficult and honestly not super well understood. So in Chem 222, we're only going to look at crystalline solids. So automatically, I'm pulling a lot of amorphous substances out, only looking at crystalline ones, but for the remainder of this time, that's going to be a good way to focus our energies. So we're only looking at crystalline solids. Crystalline solids are nice for this discussion because they're locked into what's called the crystal lattice, which means repeatable parts that are pretty close together. This is the classic positive-negative interactions we've seen since Chem 221. These have really strong intermolecular forces. The ion-ion force or metallic force, depending on what you have, we're going to consider those to be the strongest of the intermolecular forces by far, stronger than ion dipole, stronger than hydrogen bonding, stuff like that. These forces are so strong that it makes them very highly ordered. They're rigid and incompressible. So once you have them, you're not going to change their volume or something like that, like you could a gas. Crystal lattices exists as lattice points in an overall kind of larger parameter of where they are. So the little black circles and white circles right there represent, if you will, like cations and anions. And a scientist studying solids is really going to try and focus on where is the unit cell. And a unit cell is nothing more than the smallest repeating internal unit. And it has the characteristic of the solid itself. Now, again, the amorphous solids, which we're not talking about, they don't have unit cells, so they're really tough to do, and that's why that's way beyond where we can do in Chem 222. But if you have a crystal lattice, you can find a unit cell, and there's different ways to interpret unit cells. The little green box is one type of unit cell down there where you have a black atom in the middle of the four white ones, but you could also have the kind of tan square one there where a white atom was inside and black atoms are on the outside. And I've drawn their 90-degree angles, but you can have them at all kinds of weird angles and stuff. The math part here gets kind of crazy. If you're a fan of geometry, you will love unit cells because unit cells are definitely dependent on angles and lengths and stuff like that. There's a whole bunch of different, what they call brevis lattices. There's 7 main types of them, and there's the names for them, and there's a little picture there kind of on the left-hand side. Each one of these is worthy of a lecture unto itself, all right? And they're really cool. In my graduate school work, for example, I used to look at some examples of orthorhombic unit cells, and those were really cool. If you look there next to orthorhombic, you can see that all of the angles, alpha, beta, and gamma, they're all 90 degrees, but the lengths of the sides, A, B, and C, were all different. So there was some interesting geometry kind of going on there. In Chem 222, we're only going to look at the cubic, which is also known as isometric unit cells. And if you look down here at what makes an isometric or cubic cell, you have to have all the angles be 90 degrees, and all of the lengths of the sides, A, B, and C, they're all the same. So this is the simplest kind. It's probably, I would argue, maybe more common, but I don't know if that's fair or not actually to say. But what I do want to focus on here is that our discussion of solids is going to be very, very limited. We're only looking at crystalline solids, not the amorphous ones, which are hard to predict. And of the ones that we can predict, we're only looking at the cubic unit cells. We're not looking at the other kinds. In future chemistry courses, I encourage you to check out the other ones if they come up. But for right now, we're just looking at some simple examples to get an idea of how this stuff works. So in a cubic unit cell, which is only one of the 7 types, all right, all of the sides are equal lengths. So A, B, and C are all the same, and all of the angles are 90 degrees. If we wanted to find the volume of this cube, then A times B times C would equal the volume, and if A, B, and C are all the same, you could take the one side and cube it to find the volume, and that'll be helpful to us later on. Because our angles are all 90 degrees, we don't have to worry about sines, cosines, stuff like that, which is also kind of a bonus, to be honest. So again, we're picking essentially the simplest of these unit cells just to figure out how this stuff kind of works out. There are 3 types of cubic unit cells, and the first kind is called a simple cubic. So this is like a subset of the simple cubic of the cubic unit cell. And the simple cubic looks like that. All of those green dots there are like types of atoms. The second kind is called a body-centered cubic, and the third type is called a face-centered cubic. So we're going to abbreviate these SC, BCC, and FCC. Body-centered cubic has an atom inside the cell, all right? If you look at the inside of the simple cubic, there's no atom inside. But when it comes to the body-centered, there's like one right there. There's actually an atom inside the body of the cell, and that's why it's called body-centered cubic. Neither face-centered nor simple cubic has it. Now, face-centered cubic has an atom on each face of the cube. So I just circled the one on the top, if you will. There's also one here kind of facing us here, and there's one right here on the kind of left side. All 6 faces have an atom on their side, and that's why it's called the face-centered. So simple cubic is just the atoms in the corners, and that's it. Body-centered and face-centered have the atoms in the corner as well, but body-centered has an atom literally in the middle of the cell, and the face-centered cubic has an atom in each face of the cube, and that's what makes them different.
A simple cubic unit cell has one atom at each corner of a cube. The cells stack together to form a solid crystal, the overall shape of which has square edges. Each ion is shared by 8 different but connected cube cells. The arrangements of body-centered cubic and face-centered cubic unit cells are similar but more complex.
All 3 of the simple cubic unit cells had atoms in the corner of the cell. And those atoms in the corner, I want to point out that those atoms are actually shared by 8 different unit cells. So in the little animation right there, the yellow atom is not part of one particular cell. It's actually part of 8 cells. And so you can kind of see over here on the right that the little atom right there, it's like in this corner, this corner, this corner, this corner, etc., etc., etc. So when it comes to those atoms in the corners, we claim that they are 1/8 inside the cell, and that's going to be really important. Most of the atom is not in the cell. It's in the other 7 cubic unit cells right around it. This is the joy of the 3-dimensional cubic unit cell. So just realize right now that the atoms that are in the corners right there, those are only 1/8 inside the unit cell, and that's going to be important. So here's the simple cubic unit cell. And you can see in the animation on the right, it's like kind of like you're taking a chainsaw and you're cutting off the parts that aren't in the unit cell. And so each of those corner atoms, 1/8 is left in the cell, and the other 7/8 were essentially shaved. So when people talk about the number of atoms in a simple cubic cell, you have 8 atoms where there's 1/8 still left in the cube. So 8 times 1/8, simple cubic has 1 net atom. All right. So every time we talk about a simple cubic, you should think that there's 1 net atom. Technically, it's 8 times 1/8 atoms, but net is 1 net atom. Now, the other thing that we'll talk about more in lab is that it's going to be nice, because we're going to think about volumes and stuff, to think about the edge. Remember, in simple cubic, length, width, and height are all the same. The edge of a simple cubic cell equals 2 times the radius of the atom we're looking at. And that will be important coming coming up as well. So simple cubic unit cells have one net atom, and the edge equals 2 times the radius. This is the body-centered cubic. I'm going to shave off the parts of the atom which aren't in the unit cell, and when you do that, you're going to see that there still are the 8 times 1/8 atoms, those ones in the corner, but the body-centered also has an atom directly inside the body of the cell, and that stays there. So when it comes to numbers of atoms in the body-centered cubic cell, you've got 8 times 1/8, which is one net atom, plus the atom in the middle of the cell. So BCC unit cells have 2 net atoms per BCC cell. Now, I'm also going to put up here in the middle left here kind of what the edge to radius ratio is for these different unit cells. And in the solids and linear regression lab, if you're curious, we'll go over how those come around in more detail. But if you take 4 times the radius divided by the square root of 3, that's going to equal the edge of a BCC cell. And again, this comes from geometry, and you can read more about it in the lab. I won't talk about it here, but that's how you can go from the radius of one of these atoms to the edge of the cell. So 2 net atoms, edge equals 4r divided by square root of 3. That's the body-centered cubic unit cell, BCC. The third one is the face-centered cubic cell. These are also known as cubic close packing cells, and the difference between those is subtle and not something we need to go in right now. But anyway, like before, we're going to shave off the parts of the atoms which aren't in the unit cell and just look at the parts that are left over. This one in the main video takes a little bit. The lower left-hand corner shows what's going to happen. You can see how, again, you've got those 1/8 atoms, and there's 8 of them, but you also have the face atoms on this one. That's why it's called FCC, face-centered cells. And when you do that, the face atoms are still half in the cell. Half of it gets shaved off. There you can see the halves kind of coming off right now. So when it comes to the number of atoms, face-centered cubic, you still have the 8 times 1/8, which is one net atom, but now you have 6 faces with half of an atom per face. So 6 times 1/2 is 3, plus the 1/8 times 8, 1 atom, 4 net atoms per FCC cell. That's the amount of atoms that are still left once you shave it all off. So when it comes to face-centered cubic cells, 4 atoms per cell, and there's the relationship between the radius and the edge. 4 times the radius times divided by square root of 2 equals the edge. And you can read more about that in the solids lab if you're curious. But these will be important things coming up in what we're going to talk about. Here's the periodic table, and you can see the different types of metals especially that follow these examples. So the green one, polonium, the only one there in the lower right corner, is a simple cubic cell. It's got 1 net atom per cell, etc., etc. The body-centered cubics, the BCCs, basically all of group 1A, plus a couple of transition metals, stuff like that, they will have 2 atoms per cell. Now, the other ones, definitely the orangish ones there, those are the face-centered cubics, FCC, with 4 atoms per cell. Hexagonal close packing is very close to face-centered. For us right now, we're going to consider that to be the same. It's not really. You'll do more with this in a future course if this is something you need to study. But for right now, just realize that a lot of the metals you can describe through either simple cubic, body-centered cubic, or some version of the face-centered cubic. X-ray crystallography is what scientists use to determine the type of cells, and they basically have an X-ray source that they place through some kind of crystal of the solid, and there's a scattering pattern, which is what that thing shows right there. And the scattering pattern can be interpreted to give these kind of analyses, and my hat's off to X-ray scientists and stuff. It's really, really cool. But that's how they figure all these things out. There's a lot of details that we're obviously omitting in this conversation, but I know someone is anxious to know what it is, and they do use X-ray crystallography to do it. X-ray crystallography is a pretty cool field.